Welcome to The Explainer. Today we're taking a pretty wild ride. We're going to dive all the way down to microscopic 4-bit math on a piece of silicon and then scale all the way back up to massive data centers, just to truly understand NVIDIA's huge architectural leap from Hopper to Blackwell. Look, if you've been following the AI space at all, you already know that compute is basically the currency of the realm right now. But how exactly is that compute being supercharged under the hood? Let's find out.
Here's our roadmap for today. 1. The evolution of the GPU. 2. Inside the streaming multiprocessor. 3. The NVFP4 precision revolution. 4. Smashing the memory wall. And 5. The scale-up AI factory.
All right, Section 1. Evolution of the GPU. Architectural leap.
It's actually crazy to look at this timeline. Over just a few short years, we've rapidly progressed from Volta, which introduced the very first Tensor Cores back in 2017, through Ampere and Hopper, all the way to 2024's Blackwell. And man, what a leap Blackwell is. We are talking about an astounding 208 billion transistors. To even make a chip this insanely complex, NVIDIA basically had to bypass traditional manufacturing limits. They did this by using a dual-die design, essentially linking two maximum-size silicon dies with an ultra-fast 10 terabyte per second interconnect so that they function seamlessly as one single GPU.
Moving on to Section 2, inside the streaming multiprocessor, the functional heart.
So to truly get how this massive transistor budget is being utilized, we need to methodically zoom all the way into the streaming multiprocessor, or the SM. Think of it as the place where the actual math happens. It houses the CUDA cores, the specialized Tensor cores, the registers, and the cache. To put the sheer scale of Blackwell into perspective here, a chip like the Blackwell Ultra packs up to 160 of these SMs to compute AI workloads concurrently. But it's not just about having more SMs, it's really about how those SMs actually schedule the work. And there is a fundamental shift here in how instructions are executed. You see, previous architectures, like Hopper, used what's called warp synchronous execution. This basically forced groups of 32 threads to wait around and synchronize in lockstep before they could multiply matrices. So if one calculation took longer, the rest just sat there idle. Blackwell completely shatters this bottleneck. It introduces this specific new instruction called TCGen05, which allows for true independent thread scheduling. This means individual threads can issue matrix operations independently, completely eliminating those wasted idle cycles. It's a huge upgrade.
Section 3. The NVFP4 Precision Revolution. 4-bit floating point.
To really wrap your head around this, think of numerical precision kind of like image resolution. An AI doesn't need a massive, completely uncompressed 4K image just to recognize a cat in a photo, right? Well, similarly, neural networks have a really high degree of noise tolerance. They simply do not need highly precise 32-bit math to function effectively. Dropping down to 4-bit math is essentially the ultimate form of compression. It keeps the core picture intact while allowing the hardware to move data almost instantly. And shrinking that precision, it yields massive returns. By moving from the older 32-bit and 16-bit standards down to 8-bit, and now all the way down to just 4 bits with Blackwell's native NVFP4 format, we are literally looking at a 4 to 8 times throughput increase. The hardware can just physically push so much more data through the pipeline. But dropping to 4 bits does create a massive mathematical problem. That problem is represented by the number 16. In a 4-bit format, you only have 16 unique representable values. Imagine trying to map the massive, sprawling complexity of a trillion-parameter language model into just 16 distinct numbers. Normally, if a layer in a neural network spikes with a large outlier value, the tiny 4-bit format would either completely overflow or it would force all the smaller, really important numbers down to 0. The accuracy loss would be absolutely catastrophic.
So the crucial point here is how NVIDIA actually solved this. They introduced something called NVFP4 microtensor scaling. Instead of applying one scale to an entire matrix, the hardware groups the data into tiny little blocks of just 16 elements. Each 16-element block gets its own shared, higher precision 8-bit scale factor. This is brilliant, because it perfectly compartmentalizes the numerical noise. If there's a massive outlier spike, it only distorts its 15 immediate neighbors, not the entire tensor. Thanks to this architectural marvel, Blackwell retains about 99.5% of the accuracy of a full 16-bit model, but it operates at blazing fast 4-bit speeds.
All right, Section 4. Smashing the memory wall. Feeding Tensor Cores.
Okay, so if your Tensor Cores are crunching 4-bit math at record speeds, you absolutely have to feed them data fast enough so they don't starve. This is known in the industry as the memory wall, and Blackwell absolutely smashes it. Moving from Hopper's 3.35 terabytes per second, Blackwell utilizes advanced HBM3E memory to deliver a staggering 8.0 terabytes per second of bandwidth. But getting data to the chip is really only half the battle. Routing it once it's inside the chip is the other half.
To handle all that internal traffic, Blackwell introduces Tensor Memory, or TMEM for short. This is a dedicated 256 kilobyte block of memory right inside every single SM. Think of TMEM as a dedicated staging area specifically for the Tensor Cores, providing an internal effective bandwidth of nearly 100 terabytes per second. By decoupling tensor operations from standard CUDA operations, TMEM ensures that the SM's general registers don't get choked up. This allows matrix math and general-purpose logic to run concurrently without a single hitch.
So we have the microscopic 4-bit math, we have the ultra-fast HBM3E memory, and we have TMEM perfectly sorted on a single chip. But how do you actually connect hundreds of these dual-die chips together to train the world's largest models without creating a massive data traffic jam? Let's zoom out to the data center floor and find out.
Section 5. The Scale-Up AI Factory, Connecting the GPUs.
This right here is the GB200 AI Factory. Because standard PCIe lanes are vastly too slow for modern AI workloads, NVIDIA utilizes their 5th-generation NVLink. This allows up to 576 Blackwell GPUs to communicate bidirectionally at 1.8 terabytes per second. It essentially forces hundreds of distinct GPUs to act as one unified, incredibly powerful superbrain. And make no mistake, this is exactly the kind of architecture required to handle the multi-trillion parameter models that are defining the very next frontier of artificial intelligence.
But to actually orchestrate that, you need some serious infrastructure. Behind those sleek racks, you'll find intense networks of cabling and NVSwitch hardware. And because so much highly sensitive data, stuff like proprietary model weights or private patient healthcare records, moves across these cables, Blackwell implements hardware-level TEE-IO encryption over NVLink. It basically ensures massive synchronization traffic flows flawlessly, but also securely, establishing a true zero-trust environment right across the factory floor.
Furthermore, to keep this entire warehouse-scale beast constantly fed with data, Blackwell features a dedicated hardware decompression engine. Traditionally, decompressing massive databases or model weights was a job for the CPU, and that created a massive choke point. This dedicated engine pulls and decompresses data at up to 800 gigabytes per second, taking the load completely off the host CPU and ensuring those GPUs literally never have to sit around waiting to start computing.
And this brings us to the ultimate payoff. All of these hypergranular silicon innovations, the independent thread scheduling, the NVFP4 microtensor scaling, the TMEM, they all compound. The end result is a 2x acceleration in attention layer processing, which is essentially the core of modern large language models, and an absolutely incredible 25x improvement in energy efficiency per AI operation when compared to older generations.
We've literally scaled from how a single 4-bit value is structured inside a tiny silicon register all the way out to 576 GPUs communicating as a single sprawling AI factory. As traditional Moore's law continues to slow down, architectural leaps like Blackwell are sustaining Huang's law, pushing compute performance at an unprecedented trajectory. It leaves us with a pretty thrilling question to ponder. With bottlenecks continuously being shattered at both the microscopic and macroscopic levels, just how far will this architectural revolution take artificial intelligence next?